Yeah, hi peeps, it's Tess back in the old split box once again. This is a follow-up to my last main fact, fractal physics. I'm going to give you a couple of minutes of the video that I've been watching about Mandelbrot, the mathematician who, to all intents and purposes, is the father of fractals. And if you watch it to the end, you kind of gather why I think it could be important to physics, because it became very important not just to mathematics, but to what do you call it, map makers, what do you call them, cartographers or something like that, and it's something like that. He wrote a paper or a book on how long is the English coastline, and basically it's infinitely long, and yet we know that's impossible. But it's infinitely long as in it's infinitely a larger number, depending how small a measurement stick you use to measure the coastline. If you were to eventually measure it by particles, electrons or whatever, then you could probably come to basically a really, really close measurement. But if you're measuring it by miles or half miles or kilometers or yards, meters, feet, inches, centimeters, millimeters, micromillimeters, it just gets a larger and larger number. I'm sure there is possibly a finite number if you got down to measuring it, as I said, by particles. You could probably arrive at a number which is so close that going down to worm levels would be stupid. In fact, I think after you get down to meters, under meters or under feet, that's getting too sort of crazy about it. But I found that physicists, although they are fantastic mathematicians and insanely brilliant at coming up with ideas of how to see and look at particles, a particle of light, an electron, a neutron, and its path through the universe, whatever. I'm sure that they are getting to the point where it's hardly going to get anywhere by trying to refine the way we're looking at it anymore. And this is why I think fractal, looking at it from a fractal point of view, may help us to make the next step in mathematical physics. I just think it is. I think it's something that's being missed by physicists. Unless someone's already doing it, has done it, and there's a paper out there. I really should probably go and Google it and look it up. But I haven't had. It's one of my hobbies, trying to find and read and understand stuff like this. And I just haven't seen it anywhere. So if any of you know of anything like that out there, put it in the underbar and give me a link, and I will go and read it up, because I love that sort of shit. I love confusing my brain with stuff I don't understand, and then spending weeks, months, years trying to find more about it and trying to get my head around it, Anyway, I'll let you watch this video, and I hope you can understand where my last video on fractal physics links to this video, which will be fractal physics 2. Anyway, thanks very much, guys, if you do watch this, and if you do take any time to try and comprehend and understand it from my base level of understanding. I often wish I had had a better education. If I was born into a family with millions of pounds, I would probably have been at fucking, some great university and been a much more rounded and fulfilled person in his understanding of science. Maybe even have turned out to be a scientist myself, you know what I mean? But I didn't get that education. I'm struggling now to understand stuff that I was taught when I was a teenager. I'm still struggling with it. But I try to grasp the holistic view of things and have a comprehensive understanding of the stuff I don't understand. if that makes any sense. Anyway, I'll let you watch this few minutes I captured from the video, and hopefully you'll enjoy it, and it'll make you think beyond the place you are now, with your understanding of the universe, fractals, even the coastline that you see, and the way you understand lines and curves and circles and stuff, because these are extremely interesting shit. You know what I mean? To me they are, and I just hope that they are to you too. Just listen to what these people are saying, and then think about it, and think about how you view the universe as it is. I mean, even a straight line or a curve, just think about it. And maybe it'll give you a bit more understanding as well of how you can be downloading stuff and get a bad package. It's not an unknown fucking problem. They had it right at the very start of computing when they were transferring huge giant numbers down a telephone wire, which may have something more to do with the properties of the metals we were using in the telephone wires rather than the way we were transmitting the information. Although it might be something to do with both things. The energy we were using, the physical properties of the metals we were using. There's probably something in there that gives rise to the interference, the noise. Anyway, swan you fucking bad motherfuckers.
Mandelbrot's colleagues told the young mathematician about a problem of great concern to the company. IBM engineers were transmitting computer data over phone lines, but sometimes the information was not getting through.
They realized that every so often the lines became extremely noisy. Errors occurred in large numbers. It was indeed an extremely messy situation.
Mandelbrot graphed the noise data, and what he saw surprised him. Regardless of the time scale, the graph looked similar. 1 day, 1 hour, 1 second. It didn't matter. It looked about the same.
It turned out to be self-similar with a vengeance.
Mandelbrot was amazed. The strange pattern reminded him of something that had intrigued him as a young man. A mathematical mystery that dated back nearly 100 years. The mystery of the monsters.
The story really begins in the late 19th century. Mathematicians had written down a formal description of what a curve must be, but within that description there were these other things. Things that satisfied the formal definition of what a curve is, but were so weird that you could never draw them, or you couldn't even imagine drawing them. They were just regarded as monsters or things beyond the realm.
They're not lines. They're nothing like lines. They're not circles. They were like really, really weird.
The German mathematician Georg Cantor created the first of the monsters in 1883.
He just took a straight line and he said, I'm going to break this line into thirds, and the middle third I'm going to erase. So you're left with 2 lines at each end. And now I'm going to take those 2 lines, take out the middle third, and we'll do it again. So he does that over and over again.
Most people would think, well, if I've thrown everything away, eventually there's nothing left. Not the case. There's not just 1 point left. There's not just 2 points left. There's infinitely many points left.
As you zoom in on the Cantor set, the pattern stays the same, much like the noise patterns that Mandelbrot had seen at IBM. Another strange shape was put forward by the Swedish mathematician Helge von Koch.
Koch said was, well, you start with an equilateral triangle one of the classical Euclidean geometric figures, and on each side I take a piece and I substitute two pieces that are now longer than the original piece. And for each of those pieces, I substitute two pieces that are each longer than the original piece. Over and over again.
You get the same shape, but now each line has that little triangular bump on it.
And I break it again, and I break it again, and I break it again. And each time I break it, the line gets longer.
Every iteration, every cycle, he's adding on another little triangle.
Imagine iterating that process of adding little bits infinitely many times. What you end up with is something that's infinitely long.
The Koch curve was a paradox. To the eye, the curve appears to be perfectly finite. But mathematically, it is infinite, which means it cannot be measured.
At the time, they called it a pathological curve because it made no sense according to the way people were thinking about measurement and Euclidean geometry and so on.
But the Koch curve turned out to be crucial to a nagging measurement problem: the length of a coastline. In the 1940s, British scientist Lewis Richardson had observed that there can be great variation between different measurements of a coastline.
It depends on how long your yardstick is and how much patience you have. If you measure the coastline of Britain with a 1 mile yardstick, you get so many yardsticks, which gives you so many miles. If you measure with a 1 foot yardstick, it turns out that it's longer. And every time you use a shorter yardstick, you get a longer number, because you can always find finer indentations.
Mandelbrot saw that the finer and finer indentations in the Koch curve were precisely what was needed to model coastlines.
He wrote a very famous article in Science magazine called "How Long is the Coastline of Britain?"
A coastline, in geometric terms, said Mandelbrot, is a fractal. And though he knew he couldn't measure its length, he suspected he could measure something else: its roughness. To do that required rethinking one of the basic concepts in math: dimension.
What we would think of as normal geometry, one dimension is the straight line, 2 dimensions is, say, the box that has surface area.
And 3 dimensions is a cube. But could something have a dimension somewhere in between, say 2 and 3? Mandelbrot said yes. Fractals do. And the rougher they are, the higher their fractal dimension.
There are all of these technical terms like fractal dimension and self-similarity, but those are the nuts and bolts of the mathematics itself. What that fractal geometry does is give us a way of looking at, in a way that's extremely precise, the world in which we live, in particular the living world.